his research is actually recognized by many prizes, such as the Ekman Award from the American Automatic Control Council, the Control and System Theory Prize from the SIAM Society, and the Antonio Ruberti Young Researcher Prizes from the IEEE Control System Society. He is also a fellow of the IEEE and the Ifac community, and today he will give a talk on dissipative tools for convergence to Nash Equilibria in population games. So thank you very much, Murat, and please, we are very happy to hear from you.
Thank you so much for the introduction, Claudia, and thank you for the invitation too. I'm really honored to give the first of this seminar series, and I think it's a great idea, by the way, so I think this will be very successful. Maybe one of the few advantages that COVID gave us is to take advantage of remote sources. So it's kind of accelerated something that might have happened over a longer time period. All right, so I assume you see my slides in presentation mode, correct? Yes, no?
Yes, yes, we can.
Yes.
Perfect. Okay. So yeah, the talk is about dissipativity tools. The context is a little different than the usual context for dissipativity. I guess we'll be talking about Nash Equilibria and convergence to Nash Equilibria in population games. So this is joint work with my collaborator Nuno Martins, who is at the University of Maryland. And we thank the National Science Foundation for supporting this line of work. So let me go to the next slide. So this is a quick outline. So the first part will be about sort of an introduction to population games and evolutionary dynamics. If you don't have any background in games, it really is no problem, because this is pretty self-contained and mostly devoid of jargon. And then in the second part, I'll talk about why we care about converging to Nash Equilibria in evolutionary dynamics and how we can accomplish that. And dissipativity comes into play here. And then I will talk about an example, a congestion game in traffic with mixed autonomy, meaning that you have both autonomous and human-driven cars. And then we'll talk about an extension to dynamical payoff model, and then we'll give some conclusions. So here's a quick introduction to population games. So the main idea in population games is, instead of keeping track of individual agents, you keep track of proportions of agents using each strategy. Okay, and that's a good way of dealing with large numbers of players, because that becomes intractable for the standard formulation of games. And it also allows you to obtain continuum models that are perhaps a little more within our comfort zone in this community. And as we go, you will see how that ties in with some of the nonlinear systems tools as well. So one of the most popular examples of population games is what's called the congestion games. You have an origin and a destination, as you see on the left. So this, can you see my cursor too? I guess you can, or no? It's a small cursor.
Yes.
Okay, cool.
Yes.
So this is the origin, this is the destination, and these are road links, right? So there are three paths in this case, three routes to go from the origin to the destination. So each driver is faced with a choice of three routes. The choice will, of course, will be made based upon the payoff of each route. In this case, it's how little time it takes to get to the destination, right? So in this case, we don't keep track of drivers. We just keep track of the proportion of drivers using each route. So X1 is the proportion of drivers using route 1 here. X2 is the proportion of drivers using route 2, and X3 is the other route. So the standard assumption in this area is that the total flow, which is called a demand, is assumed to be constant. So you have certain number of drivers per unit time that want to go from the origin to the destination. So what that indicates is that the sum of the flows, X1, X2, X3, is a constant. And naturally, they are non-negative too. So that makes the state space in this case a simplex, as you see in the picture. And so the trajectory is that we will see later, how these choices are revised, and that leads to trajectories, dynamical models, and the dynamical trajectories evolve on this simplex. So the notion of a congestion game goes back to a book by Beckman and company from 1956. It's called Studies in the Economics of Transportation. I will take this opportunity to give you a little more background on the history of population games. So in the 1950s, and remember that's the post-war boom, lots of roads being built. So there were various commissions formed to study urban transportation problems. And so the book by Beckman and company is actually the result of the report of a commission. And even before Beckman, Wardrop in 1952 had formulated some equilibrium concepts in route choices. And the book by Beckman actually refers to Wardrop and builds on that, posing several optimization problems. So you can't find the word game in either of these works, but others made a connection to the work of Nash, which was also in the early 1950s, right? And said, look, you're really looking at a game here. Only it's a continuum, not, distinct number of players. And later on, Braes in 1968 came up with his famous counterexample in congestion games, and that led to many subsequent studies on comparing the user equilibrium, which is basically what's called a Nash or Wardrop equilibrium in this context, versus what's the social optimum. So in a road network, the Nash Wardrop equilibrium would be the equilibrium generated by selfish choices of the drivers, whereas the social optimum might be a shorter overall travel time if people would listen to what they are told to do, right? So that leads to a comparison of, how suboptimal is selfish behavior, notions such as price of anarchy, and so on. Now, in parallel, in the 1980s, some evolutionary biologists, among them, probably I would like to single out John Maynard Smith, tried to adapt game theory to evolutionary dynamics. And then later on in the 1990s and onwards, the bullets that you see above sort of merged into a more coherent research thread that we now refer to as population games. So in this framework, evolutionary dynamics are interpreted way beyond their biology context. You just interpret evolution as the revision of strategies by the users, and that leads to dynamical models. There are really good books on this, Weibull 1995, Hofbauer and Sigmund 1998. These sort of start from especially Hofbauer starts from the biology end, but the last one by Sandholm, who sadly passed away about a year ago, is really an excellent book. So we'll go back to our simplex. So I had shown you that simple example. So how do we generalize that? In general, you may have more than one population. For example, in the congestion game, you could have multiple origin-destination pairs. Or you could have vehicle types that are different. They contribute differently to capacity. They consume capacity differently, right? So you may have to separate them into different populations. Essentially, what defines a distinct population is uniformness of agents within that population and having the same set of strategies available to them, right? If you have different origin-destination pairs, those are different routes that are available to each driver. So you will have to separate them into different populations. So we use the superscript R to indicate the rth population, and we assume there are P distinct populations. But within each population, we have multiple strategies and superscript R different strategies. And basically, the state space then is a product of these simplices. So for each population, you have a simplex, and then their Cartesian product becomes your state space. So the sum of the state variables in each population is, we call it the mass of the population, R, and N superscript R denotes the number of strategies available. Everything I'm going to talk about today is, not everything, but most of it is still meaningful for a single population. So if too many superscripts are bothering you, you can just ignore them and assume there's only one population. So altogether, if you have P populations, N is the total number of strategies, and your state space, as I said, is the Cartesian product of these simplexes. So to give the definition of a Nash equilibrium, first there's an intermediate notion of a best response. And this is actually a very simple optimization problem. You could ask students and they would come up with an answer in 2 seconds. Well, maybe, depending on the student. So if I give you a vector pi, a constant vector of payoffs for each strategy, okay, what would be the distribution of the population into these strategies that maximizes the product x transpose pi? Okay, pi is a given vector. How should I choose x in the simplex so that x transpose pi becomes maximum? And the optimizer of that is x bar. If you think about this for a second, of course, if pi vector has one entry that's strictly bigger than all others, that would be maximized by going to the corner of to the vertex of the simplex that puts everybody in that strategy, right? So that's the obvious optimal solution. But now if you have two entries in pi that are equal to each other and strictly bigger than all others, then the optimum is not unique, right? So anything in the edge connecting the two vertices corresponding to the biggest entries of pi is a solution. So in general, the best response is a set valued map based on pi. So here we assume the payoff pi is a constant. In reality, it's not, because the payoff will depend on the state through a map that we will, throughout the talk, refer to as F. So F is a vector of payoffs for each strategy that depends on the distribution of the agents to those strategies. Now, we call the state x bar a Nash equilibrium if that state is a best response to the payoff at that state. So all we've done here is we've replaced pi in the previous slide with f of x bar. So x bar is a Nash equilibrium if this inequality here holds. And what that simply means is that if you're at state x bar, that means some agents are using some strategy, others are using other strategies. If a part of the agents were to, shift to a different strategy, such a small portion that f of x bar is essentially unchanged, then they will not stand to benefit from this change, right? So it's a Nash equilibrium in that sense. Okay. The natural question is, does a Nash equilibrium always exist? And it is known that if the payoff map F is continuous, then the set of Nash equilibria, which we denote as NE of F, is non-empty. And that follows from a fixed point theorem for set-valued maps. Set-valued maps because a Nash equilibrium really is a fixed point of the composition of the best response map that we talked about on the previous slide with F, right? And the best response map, as we discussed, is a set-valued map. So when you compose it with F, it's still set-valued. So, but it turns out that you will have a solution. In general, it's not unique. So that's why we talk about the set of Nash equilibria. All right, so here's an example, back to the congestion game. So that's showing us how we would construct the payoff map F in that example. So X, remember, is a vector of flows through each route. We multiply this with a routing matrix R, whose entries are 0 or 1, depending on whether a link is on a route or not. Okay, so when we multiply R and X, we get a vector of flows per link. So you've translated the flows from routes to links, right? And then you have for each link a delay function that determines how long it takes to get through that link, road link, okay? And naturally, that is a non-decreasing function. In the ideal case where your road is so wide that doesn't even matter what's flowing through it, it takes the fixed amount of time to go through it, that would be a flat line. But in reality, of course, the more flow you have, it will start getting congested and it will take longer to get through that road. That's why this is an increasing function. So we denote this the output of these functions with phi of z. Z is the link flow, phi of z is the amount of travel time through that link. And when we multiply that by R transpose, the transpose of the routing matrix, that basically adds up the travel time on each link on a route, right? So that gives us a vector of the travel times per route. And of course, by convention, we look at payoffs. So F is a good thing. It's something you want to maximize. In this case, travel time is the opposite. So we negate the sign of the travel times and we define that as our payoff in congestion games. Okay, so that's basically a static population game model. So where does dynamics come into play? Now what we're going to do is we're going to allow the players to revise their strategies according to an appropriate protocol that tells them to switch from one strategy to another. So, you know, if you're commuting from home to work every day, you may be taking some routes, but one day you discover your neighbor is you know, going to the same destination, but they have a different route and they get there sooner. And then you may want to switch, right? So that's basically accounting for that kind of revisions. So the protocol basically defines the rate at which you switch from I to J, from strategy I to strategy J. Again, you can ignore the superscripts R. They are basically indices for the population. Okay, so there are some well-known protocols that are used to model users' behavior. The so-called Brown von Neumann Nash protocol, BNN, takes the transition rate to be the maximum of 0 and these two numbers. What this indicates is if you are using strategy I, you're considering switching to strategy J, and you do that with a probability that is equal to this, okay? And that is the payoff of J, the target that you may switch to, versus the average payoff experienced by the whole population. So that's where that average is indicated. There is a even simpler protocol attributed to M.J. Smith, who's a transportation guy who should not be confused with John Maynard Smith. That would be J.M. Smith, the different character. So in this case, if you're considering switching from I to J, you look at the payoff of J, you look at your own payoff. If J is offering a better payoff, you switch with a probability that's equal to the difference. So that makes a lot of sense in practice. Okay, so there are many other protocols that people came up with. So now we compose a dynamical model that makes use of these protocols. So X subscript I is the proportion or is the total mass of users selecting strategy I. So this is talking about the rate of change of Xi. The first term is the influx of users from other strategies that are coming to I. And that, of course, has to do with rho Ji, which is the probability of switching from I to J to I, right? Which you multiply by Xj, because if there is nobody using J, you know, nobody will be flowing into I from J, okay? And then conversely, you have a flow out of strategy I into other strategies. So that's the sum of these J's. Okay, so this is basically the structure of a differential equation model that describes how the distribution of the users to different strategies evolves in time as a function of the payoff. Okay, so for each population R, you'll have a model of this form. We're going to use the notation nu for the general vector field, and of course, how that evolves depends on the payoff pi, and pi itself is a function of the x, right? So that's where we come closer to our field. We close the feedback loop, right? So EDM stands for evolutionary dynamics model. It's basically EDM1 is this model for population 1. EDM2 is this model for population 2. And as you can see, they're actually they look decoupled, right? Because XR dot depends on XR, not the other populations. So you might think these are completely decoupled systems, but they are not. They are coupled through the payoff, right? What other users are doing will affect the payoff, and that will affect our choices within our population. So the coupling comes through F. All right. So one thing to note is that by construction, the very form of the dynamical model I showed you, it makes the simplex X invariant. So there's nothing to worry about the invariance of the model of the state space in this model. It's very consistent. It's simply because if you look at the tangent cone to the simplex, the vector field that I showed you on the previous slide, by its construction, this guy here lies in that tangent cone, so you never leave the simplex. So invariance is given. That was an assumption. It was a structural property. The next one is an assumption. It's called Nash stationarity, and it's a very useful assumption that's satisfied by several protocols such as BNN and Smith protocols we talked about. So what that says is that nu of x pi, the vector, the evolution of EDM stops. It becomes 0 if and only if x is the best response to pi. Now, why is that a useful assumption? Because when I substitute pi equals f of x, basically that's the dynamical model, right? That's the right-hand side of x dot. So what the Nash stationarity assumption is saying is that you're at an equilibrium point, which I will call a rest point in this talk, because you also have Nash equilibrium that's different than dynamical equilibrium. So you're at a rest point, meaning that the vector field vanishes if and only if you are at a Nash equilibrium. Okay, so that is a nice correspondence, right? So you stop evolving when you reach a Nash equilibrium, right? The question is, do I reach a Nash equilibrium? So if you start at a random initial condition, do we actually converge to Nash equilibria? I guess for this audience, I don't need to convince you that, the fact that you have an equilibrium doesn't mean you'll go to it, right? I mean, that's what we have been living off of for many years as a field. So of course, it's not guaranteed in general. And there are many examples for these types of evolutionary dynamics where you don't converge to a Nash equilibrium. So Sandholm's book has a whole chapter describing some of these examples, chapter 9. So you can have, neutral stable cycles, you can have limit cycles, or he even goes so far to show some chaos examples that may emerge. Okay, so therefore, it is important to establish convergence guarantees to Nash equilibrium. One of the motivations for doing so is, if you look at the literature on population games, or what some people call non-atomic games, a lot of the literature assumes that you're operating at the Nash equilibrium. And then they study, is this Nash equilibrium optimal, suboptimal? What is the price of anarchy? Because Nash equilibrium describes the result of selfish behavior, right? How suboptimal is this, when compared to the social optimum? That's called the price of anarchy. And zillions of literature on that, assuming equilibrium operation. So therefore, if you can establish convergence to equilibrium, you have actually helped those guys make the case that it makes sense that you can assume you're at an equilibrium. Another criticism of the general literature that assumes equilibrium play is that, you might need too much information to be at a Nash equilibrium, right? So how do you know about the payoff of every other strategy? Information requirements may be too demanding. But what we have done here is we've shown that you don't need to know a lot of things, right? So you might be simply revising your strategy using a myopic rule, like the protocols that we saw, such as the Smith protocol, right? So you just look at somebody else and look at their payoff. If they are doing better, you switch. I mean, those are very myopic strategies that don't require very much information at all. And the evolution generated by such myopic rules can actually lead to trajectories that take you to Nash equilibrium if you can establish convergence to Nash equilibrium. So that's another reason why this line of work is important. It again gives further justification to operation at Nash equilibrium. And I should say that the global information assumptions are particularly questionable when you have large numbers of agents. You know, how do you know all the drivers know everything about the road network and the conditions and so on? And this type of analysis is therefore critical for that. Okay, without further ado, we will get it right into convergence to Nash equilibria. So first, the definition that this audience might, after I decipher it a little more, may connect to. So we call the evolutionary dynamics model x dot mu of x pi, and we treat pi here as an input. Of course, when we close the loop, pi is actually a function of x, but that's the beauty of dissipativity analysis, the modular analysis. We first look at EDM, and then we look at the payoff separately, and then we give conditions to both. When we put them together, we guarantee something about the interconnection. So we are now looking at EDM, and we call that to be delta dissipative with a supply rate characterized by a matrix M, a symmetric matrix M. If we have a continuously differentiable non-negative valued function S, which is really a storage function in the nomenclature of dissipative systems, that has the property that it vanishes when the vector field vanishes, and further it satisfies this dissipation inequality here. Okay, so there's a negative term, sigma of x pi, and we ask that that negative term can vanish only again when the vector field vanishes. Okay, so M here is a general matrix. It describes the type of dissipativity you have. The special case of 0, 1 or 0 identity, identity 0 gives us what is called delta passivity. And this notion was introduced by Fox and Shama in a paper in 1913. They were in fact trying to interpret a stability analysis, a convergence analysis to Nash equilibria by Hofbauer and Sandhol in system theoretic terms, and they came up with the notion of delta passivity. So the definition I gave you here is really a generalization of that to an arbitrary dissipation inequality where M doesn't have to be of this form. Just the way dissipativity generalizes passivity, we do the same thing for delta passivity. So, okay, so what is the delta? If we already know about passivity and dissipativity, what does delta do to us? Yes, is there a question?
Yes, there's a question about the U. Someone asked what U
Yes,
means there.
it's right here. So we can, U is in, in this inequality is just an independent variable, and this is supposed to hold for all U. But what it really represents in a dynamical system sense is the time derivative of pi. Okay, pi is the input, right? You're looking at the derivative pi dot and think of that as U. And think of the output of the system as x dot. Okay, so delta dissipativity is basically dissipativity from the derivative of the input to the derivative of the output. Okay, a little strange at first, but the benefit of this is for stability analysis, it sort of frees us from the need to know what equilibrium we are studying. Okay, when you take derivatives, it washes out the equilibrium point, and where it is doesn't really matter. Okay, so as you can see here, the storage function we are using, S of x pi, which is going to be part of our Lyapunov function, right? It vanishes when the vector field vanishes. So it's a sort of a implicit storage function that vanishes automatically when the vector field vanishes. Okay.
We have another question by Christophe.
Mm-hmm.
So I will read it. In the dynamical model, is it possible to model the fact that the capacity of the sum of roots is finite for the total population? That is, consider the case where I have two population of vehicles as car and trucks, and they're sharing the same route. Is it possible to model the traffic limit for the total population in the dynamical model or in the payoff?
So what you do if you have two types of vehicles, you separate them into different populations. Even if they have the same origin destination pair, you need to separate them into two different populations, mainly because their consumption of the resource is not the same. Okay, and we actually have an example coming up about that. There is not truck versus vehicle, but it's autonomous vehicle versus, you know, human-driven vehicle. And we can come back to this question later if I didn't address it adequately. Okay, should I continue?
Yes, thanks.
Thank you. Okay, so that's delta dissipativity, and we assumed that for the evolutionary dynamics model. Now, the main theorem uses that property. So suppose the evolutionary dynamics model has the Nash stationarity property that we discussed earlier and is delta dissipative with respect to the matrix M, defining the type of dissipativity, the type of supply rate. Now, the payoff appears in the feedback loop, right? So if the payoff satisfies a complementary property, which is this inequality star here, then we can declare that the set of Nash equilibria is globally asymptotically stable. And if it's more than a single point, a set, then it's basically a stability in the sense of set stability. So we're going to talk a little more about this inequality star. It is a complementary property to the delta dissipativity of the EDM. D subscript zeta is basically the directional derivative of the payoff map in the direction of vector zeta. The reason we are making it a little more complicated than you may think is needed is because the displacements in this case, zeta, have to be in the tangent cone, because those are, you know, you're not in an arbitrary state space, you're on a simplex, right? So this is actually relaxing more restrictive conditions you might come up with, because the trajectories can only move in certain directions. Okay, so it's sort of a relaxation of something simpler, which I'm going to show you shortly. So the main proof of the theorem, the main idea in the proof, is to take the storage function for the evolutionary dynamics model, which was s of x pi, and substitute f of x, the payoff, in place of pi. That's it. And it becomes you can use the assumptions of the theorem to show that it does serve as a Lyapunov function. Now, what does inequality star mean? It really means, if we focus for a moment on the special case of passivity, where M is zero identity, identity zero, you can show that, you know, this variational inequality really means that y minus x transpose f of y minus f of x is less than or equal to 0 for all x and y in the simplex. And that's why we had all these, you know, directional derivative in certain directions. That's why that, you know, that's what this term was helping us with, so that we can qualify the inequality for all x, y less than or equal to x. If I ask for this to happen for all x, y anywhere, then this is, of course, a more restrictive variational inequality. Okay, so that's one way to interpret the inequality star. And how does it tie in with the delta passivity of the evolutionary dynamics model? It really is a complementary dissipativity property, right? So I can view the feedback loop in this form. I introduce a derivative here, but I undo it with an integral here. Same thing on the input side, right? So I know the evolutionary dynamics model is delta passive, meaning delta dissipative, meaning that from the input here to this output, it has a standard dissipativity property. What inequality star does is it gives it a complementary dissipativity property. F being a static map, that really makes the product, I mean the quadratic term here, be an inequality. And if you remember the previous slide, the time derivative of the storage function had a negative term plus this uy transpose m uy in it. So the inequality star is essentially making that second term be non-negative. So that's how you make this the Lyapunov function. All right. So is it natural to expect the type of delta passivity property with these protocols that we talked about? The answer is yes. A lot of the existing protocols have actually been shown to be delta passive. And in fact, like I said, the very notion of delta passivity emerged from an attempt to give a system theoretic interpretation to an existing convergence result. So the BNN protocol is delta passive, and the storage function can be constructed in this way. And the derivation of this is not very simple, but it works. The Smith protocol, likewise, is dissipative if you use a storage function of this form. And I should also mention that, it's really a general structural property of the protocol that makes the delta passive. It's not, the nitty-gritty details of the protocol. In fact, there was a tutorial by Parks, Nuno Martins, and Jeff Shama in CDC 2019. And there they discuss, what makes the system delta passive, what makes a protocol delta passive, and generalizations of the BNN and Smith protocols, broader classes that encompass them, can actually be shown to be delta passive. So as a corollary to that, if we just focus on the special case of dissipativity where M is zero, identity zero, which is passivity, then the theorem basically states a known result by Fox and Shama. If the evolutionary dynamics model is Nash stationary and delta passive, like in the BNN and Smith protocols, and if the payoff has this inequality, basically an incremental sector type of condition, then the set of Nash equilibria is going to be globally asymptotically stable. Here's an illustration of that. So this is a rock, paper, scissors game. So there are three strategies. You can play rock or paper or scissors. And the payoff is, if you're playing rock, the payoff has to do with x sub s minus x sub p, because you gain by playing against scissors and you lose by playing against paper, right? And same thing for the other strategies. And this is a general form of the payoff where you may assign different weights to winning and losing, right? You can take them to be equal, but you could have a different level of happiness by winning than by losing, than unhappiness by losing. So that's what W and L represent. So when W is L equal to L or greater, then you can show that this inequality that is complementary to delta passivity actually holds for this game for all x and y on the simplex. Again, if you look at A plus A transpose, look at the eigenvalues, is actually not a sign definite matrix, but what saves the day is you're on this simplex, so you don't need to worry about the direction that's orthogonal to the simplex, which is the vector of ones, because the eigenvector of A plus A transpose that is positive happens to lie in that direction. So we don't have to worry about that. So this inequality holds when the displacements are restricted to the simplex. And this game has a unique Nash equilibrium at 1/3, 1/3, 1/3. That means the population is evenly spread over rock, paper, and scissors. That's the Nash equilibrium. Nobody stands to benefit from switching from what they are doing at that equilibrium. Okay, and you can show that if you play the game with revision strategies that are delta passive, then you will converge. And in fact, if you look at simulations, and of course these are simulations on the simplex, with the BNN and Smith protocols, you can see convergence to this Nash equilibrium when you fix the weights to be equal. If you choose your W to be less than L, then you lose this delta, you lose the complementary property here. And indeed, you can see that the trajectories no longer converge. So this, passivity-based stability criterion is not necessarily conservative result. So once you lose it, you might actually lose convergence to Nash equilibrium. Okay, so before I present the next example, I would like to make an observation, which will be very useful for the example. So suppose you have multiple populations, okay? And suppose that the evolutionary dynamics model for each population is delta passive. Okay, as we've seen, that's a very natural assumption for various protocols. Okay, now because they are distinct dynamical models, other than their inputs become, couples them, right? So you can show that for any set of positive weights, the full evolutionary dynamics model, this whole block here, is delta dissipative with respect to a supply rate M given by this that incorporates the weights here, W. Okay, so W is a block diagonal matrix that incorporates those positive weights. No matter how I choose those positive weights, the whole thing is going to be delta dissipative with respect to a supply rate of this form. It's very simple to show. When you're making a composite storage function for the whole block, you make a weighted sum of the individual storage functions, And you weight them with these W's, and you get the dissipativity property with respect to this. So why is this useful? It's useful because we have characterized the whole family of delta dissipativity properties for the EDM by taking advantage of different populations having different dynamic, separated dynamical models. And this family is parameterized by the weights in W. The benefit of this is, you'll see it on the next slide, when we look at the complementary property, we can relax it, okay? Because all we need now is for the complementary property for F to hold for one set of choices, for one set of weights, W, okay? Because no matter what W it works with, I know that the EDM has the corresponding complementary delta dissipativity property. So this is very much similar to what one does in robust control when you have structured uncertainty, right? So you introduce multipliers, which in this case is really W, and now you look for a small gain or passivity or whatever property you need from your dynamical system to hold with that multiplier incorporated, so that relaxes the condition that you're trying to achieve. Maybe I'll stop here for a second to make sure you understand, and if there's a question, a quick question I can answer before I move on to the example.
No, I think you can go ahead. There are
okay.
no more questions.
All right, so let's now look at a congestion game, but this time with two types of vehicles, autonomous and regular, okay? So what's the difference between them? They all look the same, right? One has an antenna, maybe, a radar sticking out, but so what's the difference? So the difference is that autonomous vehicles can maintain a much shorter headway. I mean, that's one of the benefits of autonomous vehicles, right? So you're not relying on human perception. You can actually do better. You can tailgate safely, in a sense, right? And that means you can use the resource, the road capacity, more effectively, okay, compared to a human-driven vehicle that has to keep a longer distance. So below is a model that accounts for this. So you split the flows into autonomous and regular. So regular gets multiplied by R, same thing for autonomous. That way they become flows. But what you do is you multiply the autonomous flow by a discount factor mu, something between 0 and 1, but smaller than 1. That means its contribution to the consumption of resources less. It's more economical, right? And when you add those up, the discounted flow for autonomous plus the regular flow, that is what you apply to the delay functions to obtain the delay of each route. Now, whether you're autonomous or regular, you use the same road, you experience the same congestion, so you're subject to the same travel time. So the amount of travel time doesn't change, but your contribution to it changes. So there's an asymmetry in the usage of the resource. I don't know how this went back. Okay, and this model captures that. Now, the standard model of the congestion game has the delta passivity, the incremental passivity property that we discussed before. But when we look at this, we'll lose it. But we do recover it once we use a weight here, W, that incorporates that discount factor mu. So with W equals identity, this inequality is not true anymore. But with W changed to this form, it is true. So our previous observation that was in corollary 2 saves the day, because we know that for any set of positive weights, the evolutionary dynamics model is delta dissipative anyway. So we can use our theorem and guarantee convergence to the set of Nash equilibria again. Okay, so we've lost the monotonicity property of the payoff, but a weighted form still persists, and a corresponding delta dissipativity property holds for the full evolutionary dynamics model. So the model with the discount factor that I just showed you was due to my colleagues Negar Meir and Roberto Horowitz. They published in the Transactions on Control of Network Systems their studies about the equilibrium, Nash equilibrium, and how efficient that is relative to the social optimum. So the theorem I have presented is from the paper I'm presenting basically with Nuno Martins, and there we show that in this example you can actually guarantee convergence to Nash equilibrium. All right, so the last two slides, the last two technical slides are about making the payoff dynamic also. So far we assumed the static payoff F. Okay, so what if the payoff also has some dynamics in it? So a simple example for that could be a lag filter that smooths out the fluctuations in the F. If you're using a navigation app, the travel times it's showing you, which is F really, right, is not, perhaps is not up to date, right? Or there may be a little bit of lag in it, right? So how does that type of delay factor in the convergence properties of such games? So basically what we are doing here is we're taking the static F, replacing it with a dynamical model. The only thing we ask for from the dynamical model is that it should recover F in steady state, meaning that when the vector field vanishes, when F of Qx is 0, the output pi should match H of X. Okay, so that's a natural assumption, so that we've added dynamics, but we didn't change the steady state behavior of that payoff. So all we have to do, I'm not going to go into details here, but all we have to do to make the theorem applicable is to change the inequality star we were using before, the static inequality, to dissipativity with supply rate U y transpose m uy with a negative sign. Okay. Earlier we were asking for this to be non-negative because it was static. Now we need a storage function whose derivative is bounded by this, right? So that's a very natural extension. And so the storage function we use for the payoff is denoted as Q. Basically, we ask for this inequality. Again, to decipher this, the first entry here is really the derivative of, if I go back to the previous slide, the derivative of pi, right? The derivative of pi, if you were to do it using these equations with partial derivatives, it's going to be partial h, partial q, etc. And that's what you are really seeing here. That is pi dot, and y is u dot. I'm sorry, x dot, right? Okay, so then the proof of the theorem is adapted using the sum of the individual storage functions rather than just using the storage function for the evolutionary dynamics model. Same idea, nothing's really changed. So we don't have time for this, but with this generalization, we actually, in the paper, we revisit the mixed autonomy example, and we add smoothing dynamics, a lag filter basically, to the payoff model. And we construct a storage function that verifies, that certifies the desired delta dissipativity property for the payoff dynamics. It uses functions known as Beckman potentials. It's the same name Beckman that was in the book that I started out with. Those are basically the integrals of the non-decreasing delay functions. These are convex functions. Those are known as Beckman potentials. And basically the storage function uses those functions as well as their Legendre transforms. All right, so to conclude, population games provide really many research opportunities for nonlinear systems because, as you've seen, we started with games, but by using the fact that we are dealing with continuum models, we were able to leverage tools from nonlinear systems. So this talk was as much an invitation to this community as information. Okay, and the general framework is broadly applicable. We've seen transportation applications, but there are many other network control systems to which these can be applied. Some years ago, there was a survey article in the Control Systems magazine by Kuihana and company. So that's a good resource to see many other applications. So in terms of what we are doing, we actually started looking into some transportation management problems under extreme demand situations. And unfortunately, we are seeing more and more of those situations with evacuation scenarios in California every summer, pretty much. We are covered with smoke and several towns have to be evacuated. And the roads are not built to allow the whole population to leave a town through them, right? Nobody has accounted for that. So it's a nightmare. So how do you manage traffic flow during an evacuation, there are some levers that you can use. I mean, we are working with a company called Zone Haven. They've basically broken up several cities into different zones, so you can stagger the evacuation by zones. You can reassign routes. For example, you can here see that the return route is all empty, right? Except that nobody's using it. You're not going to drive back into the fire. So there is a possibility of dynamic allocation of roads and so on. So we're looking into some of these problems, and the population gain formulation is useful. And just to finish with some further reading, the paper I presented is this. It has some additional results, an additional example also. And if you were intrigued by delta passivity, delta dissipativity, and you don't really care about the underlying game context, so we kind of extracted delta dissipativity from the game context, and we showed how this can be used to analyze stability for interconnected systems. So this is basically complementary to an earlier notion I had introduced called equilibrium independent passivity. So delta dissipativity, delta passivity is sort of an alternative to that, does the same thing, frees you from the knowledge requirement to know the equilibrium to analyze its stability. So this paper is a short paper showing how similar types of results go through. But I think there's a lot more to do just with the notions of delta passivity, dissipativity, how it compares to equilibrium independent dissipativity, or some other notions of dissipativity would be worthwhile. And this community is well equipped to do that. And I will stop here and thank you all.